you. So a lot was already said, but with a short word of introduction, I just wanted to say that I'm from Unidate, which is a Swiss-based company working in the domain of big data and AI. And I'm there for 4 years. I've started as a data scientist, but since there's a lot happened throughout the way, I'm now working also on the data engineering side and on cloud engineering, I would say. DARTS library is our in-house product. It was developed because we needed it, and we also saw that there is a huge lack of such a product on the market. And as it was said, it would be about time series forecasting. This presentation was created by the creators of the library, by Julian, my colleagues, and Francesco. I'm barely a user of it. I'm not the contributor in that library, but I'm using it, and I'm able to explain a few features of it. Yes, so we will start from intro to what forecasting actually is and why we need it. So before starting presenting DARTS, we need to know, and I will try to explain you in a few examples, what is forecasting and why it is such a universal problem. And the first thing is retail. If you consider, for example, a company that is selling anything, they always want to know how much supply they should have, they should possess to minimize the storage cost and also to never run out of supply, to always have things to sell. So they want to know what would be the demand. They want to know the future. Another example might be energy. So here we have another problem. We are not able to store it so far. And at this, up to these days, usually the problem was that they wanted to forecast what would be the demand for energy, so they will know how much energy they should produce. But now with reusable energy, we have another problem. We want to know how much we will be able to produce with solar or wind power. So this problem is even more complicated, and still we want to know what future holds. And the last example would be telecommunication. So the network providers, they always want to know what would be the peak network usage, what would be the hours, because implementing, adding new equipment is not something that can be done in a matter of seconds. So they also want to know what would be in the future. In all these cases, we have plenty of information about the past, but we need to know what the future is going to look like. And in other words, we just want to forecast, and more concretely, we want to have a time series forecast. And what are those time series? Perhaps you can imagine that this is sort of data, and what is special about it is that the indices, they are time intervals. Usually the spacing between those intervals is constant. And those values, they could be anything. There could be currency exchange rate, it could be milk production per cow in months, as we will see in a moment. And this time series, that's something that comes from hydroelectric plant. That's the electricity that was produced by it. And most of the time, those time series, the data that we have, they extend up to the present moment. And to speculate about the trajectory in the future, we need this forecast. So this may look like this. Here you can see with some confidence intervals how the forecasted data may look like. And this problem, the prediction might be, that's the most mathematical thing that will be in this presentation. It can be framed like this. The future is a function of our historical data plus some additional external data, something that we don't want to predict, not the time series itself, but some additional inputs. Like if you will imagine, stock options market, there are additional features that you should consider if you want to predict how the options will behave. Yes, so that's how you can frame those problems, but there's one caveat to it. Always, if we want to have a proper forecast, we need to have the signal in the data. The time series data, they usually consist of some trend, seasonality component, and some noise. And if there is no signal into it, there is no way machine learning model will learn anything. And so far, people were working on developing various models for this sort of problems. And luckily, at Unidate in DARTS library, we've gathered it all together, and we expose it with the unified interface. So here comes DARTS. That's our open Python library for manipulation and time series forecasting. And the focus of this library and of this presentation is mostly about forecasting, but there are some additional features also. And the main function is to go from the past data, like the one of this hydroelectric plant, into the future to have this forecast. There might be variations of these problems, and this might be approached in several ways. But before we will take a look how this can be done in code, I just wanted to outline 4 main principles that guide us when we develop our DARTS library. So the first thing is our time series class. That's the core abstraction, and that's the interface to the time series prediction. It is optimized for forecasting. We use it, in pandas, we have data frame. In DARTS, we have time series. That's the object that holds our data. Second, we have unified interface in all models. So all our models, they are scikit-learn-like. They have fit and predict methods. Third, we think that it is good to take care about both classical models and state-of-the-art machine learning approaches, because those state-of-the-art, they are cool. Also, it is always fun for our crew to implement papers, but also we need to have some solid baseline even to compare if what we implement, what we develop in this deep learning approaches is anything better than what very simple statistical model can do. And the last rule is that we want to be user-friendly, so we try to use industry standards. Like you see this fit and predict function. And also we want to have decent default values in all our methods. You will see this in a moment. Yeah, that's the last one before the demo. That's everything what is now in DARTS is quite extensive. The core is forecasting. But here I just wanted to outline that with DARTS you can do a lot of things like end-to-end process. When you are dealing with time series data, in DARTS you can discover your data, so you can do some statistics on time series, you can visualize them. Then you can also go for your data engineering, for your feature engineering, you can do pre-processing. There are some transformations on the time series possible and also supported. Then you go for your forecasting, and at the end, you can also do model evaluation and selection, even hyperparameter optimization. Yes, and now there would be a demo of how the basic workflow in DARTS will look like. So what we need for it, to explore the most fundamental functionalities, we want to, of course, forecast something. So we need a time series. That's a time series of monthly milk production per cow in pounds. And the black time series, it's our training set. The blue one is our validation set. And of course, the goal is to produce a forecast that would be as close as possible to our actual data. And now in the next slides, we will go step by step through the process how to do this in DARTS. So the first thing, we need this time series object. And time series, it might be created either from CSV, from JSON file, from pandas, or from NumPy arrays. It can be created in many various ways. Here we take this data, and we can visualize it on a plot. Simple as that. Then also on the same series, we want to split it into training and validation set as we do in machine learning, and we can either parameterize this function with the percentage of the data that goes into the first set, or we can just specify an index, like the time moment on which we want to split. Then we want actually already train a model, why not? So we will go for a very simple one, exponential smoothing. That's a window model that is doing exponential function on weights, very similar to averaging, but pretty useful. And here in 3 lines, we can instantiate the model, fit it, and do some prediction. In this predict function, we just want to give the number of timestamps that we want to predict after the end of training set. Yeah, that's what we do. And in DARTS, there's a wide array of different models. So we see that this one performed on this visualization quite good, but why not try another one? So we can go for another, again, very simple statistical theta model. And again, the same process. In 3 lines of code, we can get another prediction. And as you saw, in both those models, we don't specify any options or parameters. We don't use anything. And that's what I mentioned before about these defaults that are quite reasonable. So here we don't need to do this, and we get forecast that is pretty good. And that's how it usually works. Without specifying anything, we can obtain a decent results. But of course, we also provide the ability to specify those parameters if you wish. And here, in the case of the same model, we can give it a theta equal to 1. Default is 2. And again, to my mind, it's slightly worse, maybe, but it's still pretty OK. But of course, that's not how you judge your predictions, by looking at the plot. So we need some sort of metric to be able to say which model is better. And also in DARTS, we have those metrics. Here you can, there's again, the whole selection of metrics. Here you can see the very simple one. The first one is mean absolute percentage error, quite self-explanatory. And the second one is actually better suited for time series. It's mean absolute scaled error. It takes one additional parameter, the training data, because it is training very naive model on it, and then doing the scaling, the comparison to give the measure that would be, that later on we will be able to compare it. For now, we will stick to the very simplistic one, to mean absolute percentage error. And for our 2 models, we got the error like this. So we see that theta model is slightly better than the previous one. So now we know how to evaluate this model. And yeah, we can go with many models in the same way. But the one thing that we did here, and is not quite nice, is that we've splitted this data once. And we are going to overfit on this data if we will continue like this. That's the normal thing that happens in machine learning. So in time series forecasting, there is a little bit better way to evaluate those hyperparameters. Yeah, so to evaluate this model performance in classical machine learning, we will do some cross-validation split, and then we will be ready to iterate. But in time series data, it's not that easy because we have this chronological order. We cannot just shuffle this data because it will not work like this. So we need another method. It is called historical forecasting. And what we need to do, we just need to ask ourselves a question: how the model would have performed if it would have been trained on a past data, and also the prediction would be given for the past data. And in DARTS, we have 2 functions to do this. One is called historical forecast, and another is called backtest. The backtest, historical forecast just gives you the forecast on the historical data. And the backtest function, it goes one step further. It's calculating the error metric on it. Yeah, so it works like this. If we have our training data, we start with a subsequence that starts at the very beginning of our data. We train initial model on some length of this data, and we predict next elements. Then we extend the training series, and we predict another set of elements into the past future. And we continue like this until the end of our training series. And in this way, we can evaluate and compare models. So every model in DARTS has a historical forecast implemented on it. And as you can see here in the code, we can just call it. We provide a series. We provide where to start, what is the length of the first backtesting window. And then we tell the model how many time steps into the future it should predict, and the results look like this. So that's how we can use our DARTS to better evaluate model hyperparameters. And from this evaluation to optimization, there is yet another step. So we can try this function to search for the best model. We already know how to evaluate it. And rather than doing this manually, we would do something that is common in other machine learning libraries, which is grid search. So in DARTS, we also implemented, we can just simply define the parameters for our model in a dictionary. So we define thetas, and we also define the season mode. And then we call grid search function on the model, and we give the grid to optimize on the dictionary with parameters. Yeah, and on the left side, you can see the prediction done with the default, with the model that we've trained previously. And on the right-hand side, you can see the theta model that was obtained from the grid search. And we see that we will be, we were able to further improve our score without even looking at the validation set. And yeah, for this presentation, that would be the winner model, the one that performed the best. But of course, this use case was very simplistic. It was very idealized. Normally, it wouldn't be that easy. And we will have to employ some additional tools to produce better forecast. And here we will devote the last 10 minutes into these most advanced features that we have in DARTS. So modern machine learning from time series. So what we want to provide is to have this support for classical machine learning, but also for this, the one that is straight from the research. We don't see any unified, like one-stop shop when you can go and you will get the implementation of all the models that were released in the papers. So we want to shorten the way from the research into the production, and that's why our engineers work on re-implementing what researchers do. And that's usually deep learning. And those deep learning models, they cannot work on small data sets. They expose their full potential only when they have large data sets and many time series. And with this setup, with these deep learning models, we don't want just to give the model a time series like the one that we want to predict, but we give it a lot of various time series, so it will be able to generalize better. And then the prediction on our time series in mind is also better. Moreover, some time series, they can have many components. So for example, the patient data, when you measure heart rate, blood pressure, temperature, that's one time series, but it is multi-dimensional one. So that's something that we also support in DARTS. So the time series object can be not only like a series of scalar values indexed by time, but it can be a sequence of vector values also indexed by time. We also support external past and future data. That's the data that we don't want to predict, but it provides some additional insights into our prediction problem. And we also offer probabilistic forecasting. This means that we just feed the model to predict some parameters of distribution, and then we are able to do some normal statistic on it. And now let's take a closer look what it all means. So here the meta-learning, there's a M4 dataset. It comes from the famous competition when various machine learning, statistical and deep learning models compete in time series forecasting. And they've prepared 1,000K of time series. They are monthly, yearly, they are with various seasonality, but we don't know what they mean because they were randomized and also anonymized, so people will not cheat. They will not find those time series anywhere, and the models, they would be really blind to what is it, so people will just not teach the model on that also validation set. So here we've selected 48K monthly time series. Those here, they are not connected to each other. They are just random time series. We don't know what they are. We see that they are fairly different. Some have noise, some have some seasonality. This blue one has some trend in it. The black one to me looks like a random walk. And we can fit one model on all of them. So the model that we will fit is called NBITS. It comes from a paper from 2018. And that's the model, that's the first machine deep learning model that was better than statistical methods. Because for years, people thought that no deep learning model will do better than simple exponential smoothing or ARIMA in time series forecasting problems. That was actually not the first one, but the second one. It also beaten the first one. That was mix of it was mix of exponential smoothing and LSTM, and that this one is first purely deep learning model that was better. And what we do, that's pretty interesting because we train this model on all these time series, all those random time series, and what we do, we predict for a time series that was never seen by this model before. So the time series is about the yearly air travelers by airline, and that's our forecast. So it looks good, like for a model never being trained on this time series, the forecast is pretty nice, and this can be used like some sort of zero-shot forecasting. So we can just train a model and then apply it to any other time series, and this time series is only used as a kind of prompt for a model to continue it. And it is super fast and require no additional training. It is some sort of, I would say, transfer learning in the time series domain. Yeah, that would be about meta-learning. The next thing is including this past and future external data. So in blue, you see this target series, something that we know until now, and we want to predict into the future. But we also can add additional data, the data like past covariates that is unknown into the future, that is known until now. This data might be, for example, some measurements. And we may also add future covariates. So that's the data that will be known in the future as well, like marketing events that we've planned, or some public holidays, or some weather forecast that is also pretty, the weather forecast, we are pretty sure that it will be okay. So some deep learning models in DARTS, they are able to accept only past covariates. Some are able to accept only future covariates, but there are also models that accept both. This is very model specific, but one thing to remember is that if you train a model with future covariates, you will also have to provide them in inference time. So when you call your predict method, those future covariates also will be needed. And the alignment of indices of those time series is automatic in DARTS. And the last thing is probabilistic forecast. So here we have prepared a time series. The one in top is our time series in mind. So it is just sinus wave with some Gaussian additive Gaussian noise added to it. And the intensity of the noise is in purple. So in some places of the sine wave, the noise is stronger. In some places, it is weaker. So how can we do prediction on this time series? We know that it is seasonal, it's sinus. So we just can do naive seasonal, but it is not the best because it will just repeat all the noise from one month to another. So that's not the best idea. Another slightly better is to do statistical model. It is doing quite well in the places like this when we don't have a lot of noise added. But in other places, like here, where is a lot of noise, the forecast is not certain, so the prediction is not stable. Sometimes it has a lot of error, sometimes not. So the third attempt is to train this TCN model, it's temporal convolutional neural network, and we give it probability distribution. We give it Gaussian likelihood. We also in the fit method, we add this past covariate time series, so we add the noise intensity. And then for the prediction, we specify also the number of samples. So the model will not predict like a point prediction, but this will do a Monte Carlo sampling because it will fit a distribution to the data. So and then, as you see, here in the prediction, we will be able to plot it with some confidence intervals, and we will be able to do like the things that we can do with distribution. And how does it work? So for all deep learning models in DARTS, how they are trained when we want to do this in a probabilistic manner, they are trained to predict parameters of some distribution. The distribution needs to be chosen by the user, and those models are not fitted with mean squared loss, but we need a measure to compare the distance between two distributions. It might be negative log likelihood or some KL divergence. And yet another slide on time series. So how then this is handled in our object. So this time series, it has this index in time. It has those components. So here we see that there are 3 time series. They are multivariate, so we can keep 3 time series. And when we want to approach this from probabilistic side, we will also keep samples. So that would be, for each time series, for each time index, there would be number of samples drawn from the distribution by Monte Carlo method. Yeah, so once we have the parameters of distribution, those output of the models, we can sample those trajectories, and those trajectories will be in our time series object. And the representation is pretty generic. And on this representation, we can do various statistics. We have just distribution, so we can ask it for quantiles, for confidence intervals, this sort of things. And here there's a list of types of distributions that we have in DARTS. There's a lot of them, and it is very useful to know some details about your data distribution like beforehand, because then you are able to better select the distribution. And yeah, because various types of distribution might be used for various types of problems. Like this exponential likelihood can be used for some positive values. You also, if you know like how tails of your distributions looks like, you can pick the proper parameters for the Gaussian distributions, things like this. And this might be treated as some sort of Bayesian approach to this time series problem. Yeah, so that was the last part, and now conclusions and next steps. So what I wanted to say here is that our GitHub repo is open for contributors. We already have several releases when external people contributed. We are always super happy about this, and we welcome all sorts of contributions. We also see a lot of traction about DARTS in media, which is also making us super happy. Here are some next steps that we want to add into our DARTS. It is anomaly detection, auto-ML, and we also want to have some pre-trained models. Like, before this presentation, we also had several additional things on the list, like static covariates, but they were just released in August. Released in August. So yeah, that's on our radar for the next one. Yeah, so contributions are welcome, and thank you. Now we will have time for questions.
Yeah, I think we have time for. Well, let's make it 2 questions.
I've heard that transformers are quite a huge thing right now for time series. And does this framework support?
Yes, there are transformers in DARTS.
Okay, perfect.
That was a quick one. Any other question?
Yeah, there's even like tutorial how to use transformers in our DARTS page.
In the meantime, oh, there is a question. Okay.
Okay, I have a okay, maybe I will just start by example. Let's say that I collect the temperature data from the last year for Krakow, for example, and I would like to use this library for prediction, the weather prediction for next week. How naive this approach would be? Like, I know that it's not the best approach, but yeah, is it even possible, or is it a very stupid idea?
Like if you collected yearly data for like
temperature for Krakow, and I would like to predict temperature for next week.
Yeah, you could try it, but to me it looks like a problem that will require, because temperature is seasonal in a year. So if you have only 1 year temperature, this would be quite useless because we need to have some repeating pattern, and if the seasonality is yearly, it would be very difficult to any model to capture like the pattern. But still, you can give a try.
All right, so maybe as a parting note, because you presented the example with milk production, could you tell us maybe in 1 or 2 sentences what are the typical use cases that you need to forecast at your professional work?
So at my 2 times I was working in a project when I needed to forecast something. One, it was this typical supply chain. We needed to forecast how much things that our customers should buy, so they would be able to fulfill all the demand that is incoming. And yeah, that was pretty standard. The other one was way more interesting because we were working for automotive industry, and they were doing leasing contracts on cars. Those cars, they were leased for some time, but companies still possess them, so they were part of their wealth, actually. So they wanted to know how much they are worth. And we needed to forecast what would be the price of a car after the leasing period. And it is not like that strictly time series forecasting problem because there is like no series into it, but we needed to incorporate all approaches that are known from here because the data was structured in a time. We needed to do backtesting on it to know like what were the because our features were from a stock market, were from like the yearly production. This is all what influences the car prices. So we needed to incorporate some approaches from time series forecasting.
Wonderful, pretty interesting.